Hello everybody and welcome to another day of CS 219, day 7. We got Wednesday, July 22nd. So today we're going to finish covering chapter 4 and that will be pretty much it. And then tomorrow, hopefully we do chapter 5. So that will be, we'll talk about the reading, but that will be the reading for tomorrow, will be chapter 5 at least. Part of it, but I think it's actually a rather short chapter, so probably the entire chapter for 5. So yeah, okay, cool. So then let's get going then. So to refresh your mind on chapter 4 section 1, which we did talk about last time, we talked about two major concepts. And that is going to be both under the category of the principle of locality or locality of reference. And that was the idea that when you're running a program, the code that you are working on more than likely is going to be seen more than one time because you have a loop or something of the sort. And so we consider that to be temporal locality. And that was, again, the idea of like, if you are working on some code, more than likely you will see it again, like that, the instruction of the code. Similarly with data, if you were working with an address in memory, then there's a high chance that you're going to see that address again. And that it could be, for example, if you're doing sorting, if you're sorting an array, you're more than likely going to be moving things around within the array, which is a limited space that you're dealing with. You're not going to be randomly picking something from a completely different place in memory that you have never seen before. And so that is temporal locality. The other one that we talked about was spatial locality. And that's the idea that if you're working on a program and you're working again on an instruction, more than likely the instructions around that will be used pretty soon, especially the ones afterwards, but could also be the ones before it. It can make sense why the ones after would happen because normally your code is sequential and you're working from top to bottom. And so if you're working on this instruction, the one beneath it there's a high chance it's going to be next. When is that not the case? When you have some sort of branch, like you have an if statement that you can skip some lines, or you have a loop where you run to the bottom of the loop and then you're going back to the top. So that's where you can go out of order. However, most of the time our loop code is not that insanely big, and so you will still be working within a certain contained area of a program. And obviously, your program itself is not going to get out of that code. If your program itself is like 200 lines of code, then more than likely you will be working with those 200 lines of code until your program finishes. It's not like you're going to jump out into another program and run that, unless of course you were maybe calling a system call or something. But even then, that will be contained within that system call as well. So that's the idea of spatial locality in terms of instructions. And then in terms of data, you can think of it like you are working on a piece of data, and more than likely you're going to look at the data around that for additional processing. And again, that makes sense if you think of it like an array. You're processing the index 5 of an array. Index 6 and index 4 are highly likely to be accessed in the near future, and so it's good to have them ready to go. And so that was what we talked about last time. So we're kind of going to expand on that today by understanding a little bit more about how memory works and the idea of exploiting the principle of locality to speed things up with faster memory, and the idea of cache. Now, cache in detail gets talked about in chapter 5, but this kind of leads up to that discussion. Okay, so yes. Stop Twitch. Sorry, I had some kind of like migraine yesterday, and my head is still a little fuzzy, so a little hard to think. So forgive my slowness for today. Okay. Yeah. All right. So let's talk about memory. And by memory, I am talking about different kinds of memory. So kind of like an overview of memory in general. And actually for that one, let's look at a different picture. This one. Okay. So these are some of the characteristics that you want to consider when you're thinking about memory. And there can be different kinds of memory, and that will be what the other picture is. But before we even look at the different kinds of memory, let's kind of see what defines what kind of memory is what kind. And and some of the ways that you can categorize it is going to be in terms of its location. So is this a memory that is inside of the chip, such as the processor registers and part of the cache? Is it outside the chip, as potentially could be level 3 cache between shared processors? Is it something completely just outside of the chip area, but still within the inside of the computer, such as main memory? Or could it be something that is potentially external, although sometimes we have them inside the computer, such as like hard drives and that kind of thing? Or is it totally external? Like, is it like a CD drive or a flash drive that's external, or anything old school such as magnetic tapes, which is like back in the day how you would store information? Basically, there's different locations where memory can be, and there are different kinds of memory. The other thing that we can look at to sort of characterize what kind of memory we're dealing with is the capacity. So how much space can we use? Is this memory that is like 1 terabyte of memory? Is it 1 gigabyte of memory? Is it 1 megabyte of memory, and so on? So the number of bytes can come in very useful. Also the number of words. Now, what is words? The book does a pretty good job at explaining that in a little bullet point, and they claim that word is the natural unit of organization of memory, and the size of the word is typically going to be used to represent one integer. That's the number of bits required for that. So typically that's going to be around 32 bits for an integer. So that would mean that a one word is equal to 32 bits. Now, just as a reminder, how many bits are in 1 byte? That's 8 bits per byte. So if you have 32 bits for memory, how many bytes would that be? You guys tell me. How many bytes would it be to store a integer if it takes 32 bits of memory? So you take 8, there you go, 4. Good job. So yeah, you would take 32 and then you divide by 8, which gives you 4 bytes. Good job. Cool. So now that's of course something, that's computer architecture, right? Or actually that would be a computer organization. So because I could decide that in my system integers could take 40 bits, and then or 46 bits, and in that case things change, because maybe that's what I want to consider a word. So it's subjective based on the system. And the reason I say 46 bits is because apparently the older Cray supercomputer from it's called C90, I'm assuming that means from the 90s, I don't know, used 46-bit integer representation. So it doesn't have to be 4 bytes to consider a word. But for all intents and purposes, x86 and pretty much all the architectures that are used nowadays, you can consider one word to be either 32 bits or 64 bits, and more than likely it's going to be 32 bits. So yes, okay. So that, again, 4 bytes, or potentially 8 if it was 64 bits. And so that's what would be my word. So, anyways, block. When you so we're talking capacity. Okay. Next, another characteristic is how you can transfer information in and out of the memory of that memory device. And one of them is we can just transfer a word out, which means you can transfer the next number of bytes out at a time, or just simply 1 byte at a time, or sorry, 1 word at a time, which would be 4 bytes. Now, why would you be transferring 1 word at a time? Because how do you actually store things in the memory? Like, do you store things in terms of words, which would be 4 bytes or 8, or do you store them in terms of like whole blocks of data? And so that's when they put the word the block there. Blocks are more applied for when you're dealing with the hard drive and things like that. When you're talking about virtual memory, or also page sizes and things like that. So that's where they come with the block. So some devices you can only transfer X amount of pieces at a time. If you think about like when you have an external drive, like a USB, and you're formatting it, it asks you what is it called? I kind of wish I had just a USB to format to show you. When you click format, it asks you the size of the. Hold on. Let me plug in a random USB and click format on it. I'm not gonna really format it, but at least it's gonna ask me the settings. So let's see. Is it not gonna pop up? Or did it pop up and I don't see it? No, it did not pop up. Return. Sad thing. Anybody know? I mean, I can try clicking on format on one of my hard drive, but it's kind of a scary thing to do. You know? I know there's an option that it asks me for that, but that just seems like a scary thing to do. So, when you're formatting something, you know, you hit format and you set a couple of things. And one of the things that you set is, I think it's called like the partition, no, not partition size. It's called block. It's kind of like block size. It's on the format window. If anybody's brave enough to hit format, you will see it. Format menu on Windows. Oh, here, there's pictures of it. So I think I might be able to. Here we go. Yeah, there's a picture. Allocation unit size. That's what I mean. So here, I'll show you a picture. This is on Google. So it says format capacity, file system, allocation unit size. Okay? And this, and you put in a specific size. And then you hit start. That's what you get when you hit format. And the reason why I make that up is because this means that the small, if you have a file that is like 5 kilobits, okay, or sorry, 5 kilobytes, it's still gonna take in your USB flash drive. It's still gonna take at least 32 kilobytes. Anything smaller than this will take up to that. The rest of that space will be per se wasted. Okay, and that's by design how it works, because that's how the thing gets separated out and indexed basically. And so what I'm trying to get to is that unit of transfer is typically a block, and then it's just that the rest of it is pretty much empty. Okay, so that's something that, yeah, allocations. Oh, so you guys had it right, or maybe I don't know if you guys had it at the same time that I showed it, but either or. So we're gonna talk about Patrick too. I can talk at some point about the different formatting formats per se, and that has to do with like how things are indexed in there. I think in the book we will, when we get to how a hard drive works, which will be at some point. And if not, then we can talk about it some random day. We can talk about like different format systems and how they're compatible. But I'm assuming that it's at some point somewhere pretty soon, because we're talking about memory. So I think that's chapter 7. I mean, they talk about magnetic tapes, so I would be surprised if they don't talk about a hard drive. So if they don't talk about chapter 7, then I'll just talk about it. So basically next week. So anyways, that is kind of what they mean by unit of transfer block. Okay. So then we get the access method. Now this can be a little confusing, but in the book they have explanations of each of them. Maybe they have one actually here as well in the PowerPoint. Here, perfect. So different ways of accessing units of data. Okay, so this is actually kind of important to make sure that I spend a little bit of time on. So when you have a device that can store information like a memory device, and we're still not talking about any individual types yet, we're just kind of figuring out different characteristics that define them, which are these. One of them is going to be the access method, which means, can we just get the data? Like, how is it stored? What is the data structure of it, and how can we get a specific piece of information that we want? So one of the most simple ways of storing things is in a sequential way, which you can think of it like an array. Okay, and they're called records, actually. Memory is organized into units of data called records. And so the way that you access something in this sort of system is you have to actually traverse the thing like you're doing like linear search per se. You know, you gotta scan the entire device to find the piece of information that you're looking for that you store there. And this is for both reading and writing per se, because with writing you gotta find a spot that's empty to basically write on, or that you want to write on a specific spot. And it also points out that you use a shared read and write mechanism. So basically the same system that does the reading does the writing. So that's important because that can potentially impact performance as well. So here, I'll zoom in so you can see that better. There we go. And so because of that, access time is variable, right? If what you're looking for is at the top of the system, then you can find it immediately. But if not, you got to kind of scan down and get it, okay? And even if you know the index that you have to go to, so suppose you want to write to index 20, okay? If you want to write to index 20, it's not like you can just immediately jump there. You actually have to move a read head all the way down to index 20. Now, what's examples of things like that would use this system? Think about like a magnetic tape, like actual piece of tape that's actually moving the tape to the spot where you're trying to access. Okay, that would be an example of something that uses sequential access, like a physical magnetic tape device. I think that's the only one that really I can think of that would access like that. And they say here they'll talk about it in chapter 7. So you will talk about magnetic tapes in chapter 7. But ultimately, that's old school. As you can see, it's not very efficient because the whole idea of access time being variable is not really a good thing for us if we're trying to access information. That slows us down quite a bit. So the reason why you format, you have to choose a specific file because of it. Well, not just because of that. I mean, that's the end purpose for an end user, that you have to choose different file formats. But you can tweak around within the same OS for different format settings to have different purposes. Like for example, if you have a really large file, you have to choose a specific format. Otherwise, you won't be able to do it. Like that's one of the issues why they went to exFAT and other systems, because if your file bigger than 4 gigabytes, the addressing system that you use with the old school FAT, I believe, runs out and you can't store it. So that's actually a thing. So anyways, back to this. Again, we'll talk about storage devices in chapter 7. So we also have direct access. Now, direct access is kind of like the better version of sequential access, because in this case, even though you're still doing the shared read and write, you can jump in physically to a specific spot in it. Whereas here you have to do that linear search kind of thing. Here you can jump right in. So that is more of like, I believe will be your hard drive, your disk units. Okay, so you know where in the circle the information is stored, but you still have to physically move a reading head to that spot to read it. And that might seem like a lot of work, but that's actually how, again, hard drives are implemented, and we use them still up to today. And so access time is variable as well, because depending on how far we have to move the reading head in the disk itself is how long it takes us for us to read, which on average is going to be about a millisecond, I believe, for reading into a hard drive disk. So again, direct access and sequential access, this means you can just kind of jump right into the spot, but you still have to physically move your reading head, whereas this you have to kind of like linearly scan on a magnetic tape, you have to like rewind it and things like that. Here you can just jump right in. And again, you still use the shared read and write. So the same needle that reads information writes information. And most common example is, again, a disk drive or a CD drive too. Okay, then we move on to random access, and by the way, we're kind of going into the faster. We're going faster this way. So now we're in the third column, random access. So random access is actually how you have your typical main memory. RAM stands for random access memory. So that's kind of where that comes from. And each addressable location, as it says here, has a unique physically wired addressing mechanism. So that means that you have a direct shortcut, per se, to get to any spot in the memory. There's a straight wire. So there's no physical components at this point that you have to move. And anything that's physical component that you have to move means it's slow. Here, things are wired in, which means that you're only limited by the speed of electricity. Yeah, for the most part, I would say, okay? So any location you can pick and directly access. So it's constant time to access. It is no longer a variable time because of the distance from the thing that you gotta move. No, at this point, everything is the same time in terms of accessing. Any location can be accessed directly, and it's constant time. The time to access it, the time to access a given location is independent of the sequential of prior access. What they're trying to say with that is that it doesn't matter what you just accessed before. The next one will still take the same amount of time. Okay, so if I access address 50 in memory and now I'm addressing address 10, it's going to take me the same time that it would have taken me to access address 5. There's still going to be a potential delay between different accessing of addresses, which we'll talk about as the memory cycle time. But at this point, all we're saying is that it is a constant time to access between things. Whereas with the physical drive, in your disk, if you're accessing something here, and then the next thing you're accessing is at the complete opposite side of the disk, you have to physically spin the disk to get it to the right spot and then move the needle up and down. Whereas, say you access something in the disk here, and the next thing you're accessing is here, then you only have to move a shorter amount of time. So the previous place that you access actually matters in the disk, whereas with a random access memory, it no longer does. So that's a much better thing that we can have, okay? Associative is a little bit weird in how it works, and the book does not the best of jobs to explaining it, and I don't know if I can do better. But it's kind of like RAM in the sense that the time is constant to access things. So there's no physical movement. What uses it is cache may use it, but they don't have to use it. And so each location has its own address. You can access in constant time. But in addition to just accessing data with just an address, you can also access it based on the contents that it has. So it's kind of, if you've taken 302, kind of like a hash table in a way. That you're not just using an address potentially to access something, but you can also use a value of what is stored in that address as a way to get to it. Is SSD direct access? No, SSD is random access, but it's a special kind of random access because it's not as fast as your RAM. So we'll talk about that. But yes, with an SSD, it's a solid state memory device, which means that there's no physical parts, which means that your access time is going to be constant and no longer is it variable. So it's definitely better, which is why they're much more preferred nowadays. So anyways, back to our chart. That's what we mean by the access method. Now it became answers. Okay, there we go. So access method is going to be how we access things, and that kind of is a big defining thing for what kind of memory we want for what task. Obviously, you can see that there's an ideal memory. Ideal memory is one that's very big, that has random access or associative, I guess, if that's what you're looking for. Your units of transfer are pros and cons in that one. It could be big or small depending on what you're using for. So you'll see that there is no ideal memory, but there are some that are like almost perfect. Okay, performance. So let's talk about the performance of memory, because that's kind of important when you're picking memory, right? So we have these three things. We have access time, cycle time, and transfer rate. And we kind of talked a little bit about this the other day too, when I was talking about the system bus and how you may be able to transfer stuff quickly in the system bus, but the first piece of information is going to take time to actually arrive, and so there's that initial delay. So that's going to be kind of like your access time, so the latency. So when you're talking about RAM, it's constant time to get to information, but constant in the sense that there's still some time that it takes to actually get the information, right? That initial time to actually seek the information is going to be your access time in RAM style memory. In non RAM type memory, so basically your hard drives and things like that, the access time is going to be variable. Again, that's going to be how long it takes for the mechanism to actually move to the right spot over the tape and things like that. So that's important because it defines how quickly memory is, right? We want that to be as small as possible. That's just the initial time to get the data. The data may be able to transfer super fast, but if we have a latency issue, it's still going to be a slow device. For example, suppose that you're watching a movie. Okay, a movie is stored in the hard drive typically. It's not stored in main memory because it's a pretty big file. If you're watching it on a computer, or actually, if you're watching it on a Blu-ray disc, for example, then it's stored on a disc, right? And that is pretty slow if you think about it compared to RAM. So your access time is pretty slow. However, movies can still be watched pretty comfortably without their lagging or skipping, right? That's because once you actually get that initial pickup time and start things flowing, start feeding the pipeline with frames of the movie, then things get pretty fast. So it's only that initial delay at the beginning to start to move the disc to the beginning of the movie, and then kind of sequentially start moving in, and that of course is because the disc has all the frames kind of in a nice sort of spiral form, so once you read in the first frame, it can move kind of just a little bit. If it was all over the place, then yeah, that'd be a big mess. But that's why things like the fragmenting and things work to help this situation. But the point is that once you kind of get the thing going, start spinning up the disk and start sending information, then it's a constant flow of information and there's not a problem. However, that's because again in the movie things, you know exactly what the next frame is going to be to load. If you switch over to a different task where you're reading a bunch of different files, your access time may be really slow and things may lag more and be harder to read, or slower to read, sorry. And so access time is very important in general, but it's more important for things that are not stored sequentially, because then that can be all over the place. Otherwise, once you get that initial delay, then things are good. Okay? So that's the deal with access time. Now, what is memory cycle time? Memory cycle time is how long it takes once you've read something to be able to read the next thing. So even in RAM, there's a certain delay. It's a constant delay, but there's a delay between reading one word and reading the next word. And that's because you have to kind of clear out the system from the wires have to kind of clear out before you can access the next thing. And that's what they mean here when they say additional time may require for the transients to die out on the signal lines or to regenerate the data if they're read destructively. And so that process takes time. And so you could have a super fast access time, but after you access something, the whole system needs to cool down. And if that's the case, then you're still going to have bad performance, because you want to not just be able to read something quickly, but you want to read any follow-up items quickly. And so that cycle time, it's mostly used when you're talking about RAM, but it's sort of the cool down phase. Imagine if the laser that was reading in information from a disk had to cool down between different scans. Like it shoots a laser and they have to cool down so it doesn't overheat and then shoots it again. That would be kind of like the equivalent cycle time for a hard drive disk. So basically, the memory cycle time is going to kind of be the access time plus the cooldown time. Okay, so it's kind of both things together. Finally, we have the transfer rate. The transfer rate is mostly connected actually to the system bus and the memory, but that is once you find the information that you're trying to read, you need to actually send it out into the pipeline, into the system bus to be sent to the CPU, right? That time it takes to do that and the time it takes to go to the CPU, I suppose, would be your transfer rate. And typically that's going to be just your cycle time, because then once it's in the system bus, it's kind of beyond you and it doesn't matter what kind of memory you have. But in some devices, like old devices, it could have taken a long time to transfer things. So again, I think I said this example yesterday, when consumers are testing like SD cards and things like that. If you're testing an SD card, You know, the people selling you the SD card may claim you have very fast transfer rate. However, that doesn't tell the full story, right? Because if your access time is really slow, then it doesn't matter if you have a really good transfer rate, because you're kind of gonna have the bottleneck somewhere else, right? So you know, or sometimes like the transfer rate is really high when you're transferring one really big file, but when you're transferring a lot of little tiny files, the transfer rate goes down, because even though the transfer rate is per se high, you know, your access time and your cycle time are slower, so that slows down the entire system. So it's a, you know, it's sort of a three-way performance parameters to really compute how good of a performance something is. It's not just one number is not going to define this. You know, you need multiple numbers for that. So that's performance. Physical type, I guess, also is a way to characterize something. So random access memory and SSDs are going to be dealt with semiconductors. And then other kinds of memory, or cache as well, I suppose. Cache, registers, all of those things. Magnetic, of course, you got your tapes, and I suppose also hard drives technically are magnetic. And a mixture of magnetic and optical. And that's another type of storing information. Again, I kind of really want to go sidetrack and talk about how hard drives work, but again, we'll talk about that later. So yes, I'll explain how that actually works with the magnets. Really just want to go there for some reason. And then of course it can be a mixture of magnetic and optical. So that's kind of your physical types. Physical characteristics is also very, 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 very important. And what does volatile and non-volatile mean? That means that if you lose power with volatile memory, you lose the information. You have to feed it constant electricity, and sometimes you have to refresh it as well to be able to maintain the information. Non-volatile means that if you cut the power, the information will remain. So an example of non-volatile memory would be like your SSDs. An example of, or a hard drive actually too. An example of volatile memory would be RAM, basically. Your RAM or your cache. Those things, if the power goes, you know, we talked it's not immediate, but within a second or a few seconds, all the information will be completely gone. And even within a half a second, some of the information is already gone. You know, you're at that point, you're kind of like in recovery zone. So that's what they mean with volatile and non-volatile. I can't remember where that's in the book, because I had a bit of an example with that. But where is that volatile stuff? Because I had a discussion that I wanted to mention. Oh, yeah, here we go. Physical characteristics. Semiconductor memory, maybe the volatile and non-volatile. Yes. Okay, so this is the other thing. ROMs. So a ROM. What is a ROM? ROM is read-only memory. You may know ROMs if you think about like the emulator days with Nintendo and things like that, where you download the ROMs for a game, and they call them ROMs. But what ROM really stands for is read-only memory. So some kinds of memory you can't write to them. You can only read for them. They're like hard-coded per se, and that will be a semiconductor type of memory. And when is that useful? That's useful in embedded systems when you don't really need to change what's stored in the program that is always going to be running in this IoT device and things like that. But also, you know, think about it like a video game. You know, when you buy a system cartridge, you know, or well, nowadays, what would be the console that would use that? The Switch, the Nintendo Switch, that uses little fixed little SSD looking things. And so those are ROMs, because you don't want to accidentally delete your games. And so, you know, that it's memory, it's semiconductor memory, so that it's relatively fast, but it is not erasable. And so because of that, it's non-volatile either, and it's always available, you know, and you want it to be fast. So ROM is read-only memory, and it can be quite useful at times. Magnetic surfaces are non-volatile, and so here we go. So in volatile memory, information decays naturally or is lost when electrical power is switched off. In non-volatile memory, information once recorded remains without deterioration until deliberately changed. No electrical power is needed to retain information. So I kind of disagree with the without deterioration, because the fact of the matter is that they claim that a couple of things that are technically non-volatile memory do degrade with time. I believe a hard drive is not going to last you longer than 20 or 30 years in storage if you don't actually use it. The magnetism will eventually fade away because of Earth's magnetic shield and whatever. You know, it like actually has an effect on this thing to decay it. Magnetic tapes like VHSs degrade as well within like 15 years or so. You start getting grain on them. So I would argue that it's not necessarily without deterioration. However, some hard drives are claimed to last over 1,000 years and things like that. So that's yet to be seen, of course. Why do SD cards most of the time are slow compared to an SSD? Aren't they both similar? They are very similar in design, and SD cards are pretty fast actually, but it's just one piece of the picture. Like you gotta consider like the reading device that is working with an SSD card, and even then, there are different kinds of semiconductor memory, and so it's kind of hard to compare like side-by-side RAM with SSDs because there's different kinds of RAM as well. There's DDR1, DDR2, DDR3, DDR4, maybe there's a DDR5, I don't even know. But so it depends on which one they decide to use, and of course that's going to affect the price. And also, unlike RAM, but more like SSDs, it has to be non-volatile because you know you want the information to be kind of permanent there, and so that's going to affect it as well. And even within SSDs, there's different kind of SSDs, as you guys know. There's they're called nowadays NAND, and what's the other one? I don't know. It's probably on the book. But there's a lot of, and that's what we're going to get to in a second here. The idea that even within like these categories, there's different types of memory and different speeds, and that's going to be really define what you want because faster access time, you know, which is, you know, quicker read time, there's a greater cost per bit. And then on the other side of things, if you want greater capacity, you slow down access time. So you have to find a middle ground for a camera where you want a lot of capacity, but you also want to maintain a relatively fast access time because that could be read or write. However, the one good thing is typically when you go up to the greater capacity, the cost of per bit for storage goes down because when you buy like a 512 SSD card or SD card, the cost per number of bit goes down compared to if you buy something like a 12 or 8 gigabit card. You know, and that's just because, you know, bigger is still more expensive, but it's not always twice as expensive. Like if an 8 gigabyte SD card is $5, a 16 gigabyte SD card is not $10. It's probably like $9 and so on. So anyways, that's kind of the explanation for that. So anyways, those are the physical characteristics, whether it is volatile or non-volatile, which means if power goes out, does the information stay, and whether it's erasable or non-erasable. Volatile memory by nature is erasable. Non-volatile memory is the one that can be erasable or not. Erasables will be a disk drive or an SSD drive or SSD is mean solid state drive or SD card. Non-erasable, that will be your ROMs, okay, your read-only memory, which is like again what like something like a Nintendo Switch cartridge would have. Finally, organization. That one it says we will talk about it in chapter 6. So that basically is the physical arrangement of the thing. So we'll defer discussing that until chapter 6, if we do chapter 6, because I think we will, but can't remember if we do that one. So yeah, that's basically 4.2, and I suppose transfer rate. We should talk about a little formula there. I'm sure the TA will go over an example with that, but let's see if it's here. I don't think they have the formula here. Okay, so I'll just write it on the tablet. So there's a couple of formulas in this chapter that they're good to know. And for example, this one is relatively trivial, but Might as well put it here. So let me just write what these variables mean. And then R is the transfer rate. In bits per second. So again, transfer rate is how quickly you can transfer information in and out of memory. And typically for random access memory, that is going to be 1 over the cycle time. But for non-random access memory, which is something like a hard drive or things like that, this is the relationship that typically holds. And what this means is that you take the number of bits that you want to transfer, and then you look at the transfer rate in terms of bits per second. So for example, suppose that you're trying to transfer 1 megabit. Okay? How much is 1 megabit? That can be 1,000 kilobits per se. And so suppose that your transfer rate is well, here, I don't want to do hard math here. So let's say we want to do 100 megabits, and then the transfer rate happens to be 10 megabits per second. Okay? This is trivial math, right? You can do 10 out of 10 per second. You got 100. How long is that going to take? 10 seconds, right? Okay. So in addition to this, you also need to add in the access time. The access time is how long it takes you to find the information, and that is, of course, in non-random access. And non-RAM is going to vary, right? Because again, if looking at a disk and here's one piece of information, and here's another piece of information, and here's another piece of information that you need to transfer, you have to move there, then you have to move there, right? And this takes maybe, let's exaggerate these values. Let's say this takes half a second, and then this one here takes like 0.3 of a second because it's a shorter distance, So you have to actually average these values together to kind of get the average access time. And you can use any of your averages, harmonic, geometric, whatever, but you need to do some sort of averaging. And so when you average that, you say that it maybe takes you 1 second in average to access all of these things. And so you have to basically add that to your 10 here to finally get the average time to read and write n number of bits. And so that's kind of what they're talking about there. So it's a useful formula to have. Okay, so great. Okay, so now we can move on to 4.3. So that will be the memory hierarchy. So let's talk about this picture here. Okay, so actually I just talked about this a minute ago with the access time. So surprise, surprise, like pretty much a lot of devices in the computer, when you go out and buy something, better is more expensive, right? That typically tends to hold. You want a faster computer, it's going to cost more. Now, we have Moore's law that helps us out in the long run, right? Every 18 months, we get twice the power for half the price. Or sorry, twice the power for the same price, But if you don't want to wait 18 months and we can get something better now, we may have to pay a little bit more money. And so with RAM, you kind of have the same situation where as time progresses, it costs the same, random shortages aside and things like that happen. It typically costs the same, but it gets a little bit better. And it gets better in the sense that it increases in capacity, but also it increases in access time, which means it gets faster and it gets bigger, right? And the price stays relatively the same. So let me switch over to that. Okay. And so within that, though, there's a big dilemma, because when you want something faster, it increases the cost per bit. And by cost per bit, I'm saying that if I have a 1 gigabyte, well, nowadays bigger than that, okay, 8 gigabyte RAM stick, that it has a really, really fast access time, higher frequency and all that. And then I can also, that's one option that I can buy for my build. The other option is I could buy a 16 gigabyte stick of RAM that's a little bit slower, you know? And so that one has more capacity, but it has slower access time. So which one will benefit my build more? And it truly depends on what you need to do. Do you need that much capacity? And if you do, then you have no choice. You have to get the bigger one. If you don't, then perhaps you might actually be okay with using the 8 gigabyte stick of RAM, because you don't need to use 16 gigs at once, and you can increase that access time, right? And so the thing is, when you get that faster access time, it's going to be more expensive. Furthermore, when you have greater capacity, things go down in price. But again, that's sort of secondary to the access time. And so you have this sort of give and take between those three things, that there are trade-offs between those key characteristics. And it's kind of a dilemma from a designer's point of view, like, in the designer's ideal world, they would like to have a technology that has lots of space, it's very fast, and it's very cheap, right? Those three things: fast, cheap, and big. Big, fast, and cheap per se. If I as a developer company, as a manufacturer, could produce a 1 terabyte stick of RAM that was the fastest available, and it cost me like $1 to make, I could sell it for $100 and make tons of money, and it would still be way cheaper than the competitor, right? That would be, of course, the ideal world. Everybody would love to do that. There's capitalism would shine in that. They could sell it for more expensive, but then as competition grows, they have to go down in price. So the thing is, though, that we don't live in that perfect world, and we have to give and take. And because we have to give and take, when we end up kind of in the situation is, we are going to have different kinds of memory within the same device, so that we can try to gain advantages such as access time in smaller pieces of memory. But for those requirements for those situations where we require a lot of memory, we can have other slower memory that's bigger in capacity. And so by sort of mix and matching these different kinds of memory, we can kind of try to average out where we have an increase in capacity, but still try to maintain the cost per bit low, while still having fast access time. So, if we can't, suppose that we want a computer that can store 1 terabyte of information. We can't afford 1 terabyte of memory, but we can afford maybe 8 gigs of RAM, and then have a 1 terabyte SSD, which is still going to be okay. It's going to be fast, but it's not going to be as fast as memory. And then we can kind of get away with that, because we will sort of have the advantage of having fast access time because we have the memory, but still have big capacity for when we need to with the SSD. And of course, if we can't afford an SSD, then we get into something like a hard drive, right? But a hard drive is going to be cheaper, but have slower access time. And yes, we do want to have that balance, right? Although here I'd say we want to tip the balance in our favor, because screw the price, The price can be on balance as long as it's cheap in that side of the balance table, okay? So the 4 things, and there should be well, they have the thing about faster access time, but they don't have the 4 points in here. So let me write them down just so we can have them here for reference. They're on the book. But the 4 things that are kind of going to dictate what we're trying to do is, we say A, B, C, and D. And hopefully you all read this. The author keeps referring to these letters A through D, so as you read it, which is what he's referring to is these 4 goals that we're trying to do. Okay, so it's a little bit confusing at first when you're reading it and you're like, why does he keep talking about A and D? But that's what he's talking about. So decreasing cost per bit, increasing capacity, increasing access time, and then decreasing frequency of access of the memory by the processor. Okay, so those are the 4 things that we're kind of aiming to do. We want to decrease the cost per bit, which means more space, more memory for less price. We want to increase that capacity, so those two kind of go together. We want to increase access time, so it means we want to keep our memory fast. And increase could be a misleading word. I'd flip it around and say we want to not decrease the access time, okay? Not necessarily increase, but not decrease. Because by going by cheaper stuff, we kind of lower the access time. And then we also want to decrease how often, I forgot a C with access. We want to decrease how often the processor needs to actually access any of these things. Okay? So that's our goal. And we have a plethora of, it's like a buffet of different kinds of memory to achieve this. So this is what is known as the memory hierarchy. And so the top of this is going to be the fastest, bestest memory, but it's typically really small. And then the bottom of this is going to be, ignoring that last bottom one, like, yeah, that's nobody uses that anymore. Ignoring that last bottom one is going to be the biggest, cheapest memory, but slowest, okay? And so, obviously, we're trying to sort of have a little bit of everything, like a food pyramid kind of thing, okay? What type of memory supercomputers mainly have? Supercomputers and your general purpose computers have the same exact kind of memory. In fact, in the book, they talk about one example of that in the last section of this. So when we get there, we'll talk about that. But yeah, they gave an example with, I think, some chip. What is it? I don't know. It's at the end. I'm reading it, but it's just gonna be supercomputers don't necessarily use different memory than what we have. In fact, they use cheaper stuff sometimes because they have a lot of it. They have 1 terabyte of RAM that they share between the node, or potentially a drawer, but it's still gonna be the same kind of RAM that you use, but maybe it's DDR3 instead of like DDR4. So yeah, I really like the pyramid because the size of the blocks relates to the capacity. Hey, yeah, that's a good point. The bottom ones look bigger, so. Yeah, and the distance is a little bit misleading because technically a flash drive could be further away than a disk drive physically, because it's a flash drive you're plugging outside. So outside of the flash drive example, the distance does apply, the distance rule, that as you go lower, the distance gets bigger. So anyways, let's start kind of looking at these. So the fastest memory, fastest guy in the West or whatever, is going to be your register memory. Now, how is that? What is register memory made of? It's they say it right here. It's of course going to be volatile memory. It's random access, and also kind of correlate, by the way, is this picture here, the one next to it. That is going to be increasing cost, increasing the access time. So that means that the higher here, the further back is the fastest access time and the highest cost. So you can see that it's a little curve. I guess it goes this way. Okay? But let me see on the book where they mentioned that. It looks so weird because when I was reading the book, I was reading it. So I finally got a digital version of the book on the Vital Source. And I was reading it in black and white so to not hurt my eyes. So the book looks different now that I'm looking at it in an actual print version. But at some point they were mentioning registers. Here we go. Registers, contemporary machines. Okay. I can't find it. But anyways, it's made in the wafers of the semiconductor. So it's memory, but it is inside of the chip, as it says, on-chip storage. And it's going to be the fastest memory that you have, which is going to be a bunch of transistors that are very, very close to the processing unit, okay? Could be SRAM style of chip as well, but I think it's more complicated than that. I just cannot remember, for the sake of it, which one it is, okay? So here we have a question. So is there such a thing as the optimal memory, or does it differ depending on what you want for your computer? I would say that the optimal memory would be one that is non-volatile, super fast access time, big capacity, and very cheap. No such thing exists. But you could have a combination of 2 types of memory. You could have like SRAM type of memory, you know, as your main memory, and you could put it as close as you could to the chip. That's achievable. And then you could have a non-volatile, which the fastest we can think of is potentially solid state memory, like a SSD. And I suppose that would be the ideal combination with today's existing resources. However, as we're going to see here with cache and with hit or miss and this kind of thing, that's okay. It's okay. We're not going to lose that much efficiency by having a mixture of things, as we'll get to pretty soon. If you could have a terabyte of cache, I think that'd be the most optimal. The thing with that is that you will see that it's optimal by very little. Like it's a curve, and you sort of lose edge after a while. And that's actually one of the last things that we'll hopefully talk about today, when we get to the hit or miss rate. And they reference some papers that discuss that, and they say, well, we'll get to it because I don't want to confuse you guys. So we'll get to that. How would cloud storage fit into the pyramid? It would be at the bottom along with other database memory here. So that would be at the outboard storage here, not necessarily the offline. The offline thing, you can kind of ignore that nowadays. What this is really saying, well, here, let's go for the top. So we got registers. Again, those are in the chip. And we got multiple cache levels. Using SRAM for the lowest level, so L1 and L2 cache, we'll use the SRAM. And then typically the L3 cache. Actually, in your general purpose machine, L3 cache probably uses SRAM. However, since you mentioned in a supercomputer, the L3 cache could be pretty big, like 600 megabytes or something. And then that would actually use EDRAM, okay, which is faster than DRAM, but slower than SRAM, okay? So SRAM, better than EDRAM. But both of them are still better than just DRAM, okay? So that's what you use sort of on the chip. Or, again, misleading here because level 3 cache isn't really inside the chip. It's not inside the cores. It's in the processing unit, but it's not in the core. So make sure you understand that registers and L1 and L2 cache are inside the core, whereas L3 is shared between cores. So it can potentially be outside the cores, but still in the processing unit. But when you got multiple chips together, you might still have like an L4 cache or even an L3 cache that's outside the entire chip completely, but still within the same area where you have the multiple chips. Okay, so yeah, from there we get to main memory, which is on the computer basically, but not inside the chip area, and that's going to be your RAM potentially. And you have DRAM, which means dynamic random access memory. SDRAM, which I don't know what the first S stands for actually. By the way, the E in DRAM stands for embedded. So that's embedded dynamic random access memory. Now what does static, yeah. So by the way, the S in this means static random access memory. So I don't know if this means static dynamic random access memory. I don't think so. I'm not sure what SDRAM stands for. We could probably Google it and see what it stands for. I don't think it means static random access. So I know SRAM means static random access memory, and EDRAM means embedded dynamic random access memory. DRAM means dynamic random access memory. SDRAM is the one that I'm not sure. So let's see. SDRAM acronym. Double data rate. Oh, well, that's the DDR one. The DDR one, I guess might as well cover that one. So DDR RAM stands for double data rate synchronous. Oh, so that's probably what it means, synchronous dynamic. So that's what probably SDRAM stands for, synchronous dynamic random access memory. And then DDR, which is you're familiar with, is double data rate. DDR it's sort of an improvement. So you kind of want to have DDR. That's why nowadays it's the popular thing. So anyways, from there we get into the sort of slower devices, which is your but non-volatile. So this is when we make the jump to non-volatile with solid state memory devices like SSDs or USBs and that kind of thing. And again, USBs are a little misleading that they're here because they can be external too, right? Unless you permanently leave it plugged in, like a Raspberry Pi or something. So that's your solid state, and then you get your virtual memory file and database memory. That's going to be your hard drives. And I would say that's your external storage as well, like offline storage, like long-term storage, like big hard drives that you keep for slower stuff. Because nowadays most computers we just get an SSD and we're calling it a day, right? But you might want to have a hard drive as well for the non-critical stuff, like just a bunch of pictures and movies and things like that. The offline bulk memory, so cloud computing, as you asked, will be somewhere around here, between these two, I would say, because cloud computing is going to be slower than anything remotely near you. Even if you have an SSD in your cloud computing system, it's going to be slow trying to access that over the internet, basically. So it's slower than any kind of hard drive that you could have. I suppose nobody wants magnetic tape, so I do think that there are actually data centers that will rent you magnetic tape data storage for super extreme cheap. Like I've read that before. So I suppose that in theory this still exists because nobody wants it anymore, but there's a ton of it still left. So I think some people were smart enough to start a business saying, like, we have a bunch of magnetic tape that nobody wanted, so we can actually offer it to store data, and you can store like for extreme cheap. So I do think that there's companies that do that actually. Let's see, quick Google and see if you can find one. Magnetic tape storage cheap. Here's a paper that says why the future of data storage is still magnetic tape. Ignore these people, they're crazy probably. Here we go. Yeah, tape is here to rescue big data, so like I said, there's still tons of it out there, so it's better than throwing it away. What makes the PS5 SSD so special? I don't know, that's marketing terms, but there is an idea of caching that doesn't just apply to CPUs. Caching can also be applying for disk drives and even for main memory. And what they could be doing with the PS5 SSD is they could be saying, and I haven't read much about it, I just heard like the internet kind of complain about it, is they probably have some sort of cache system that they're trying to kind of sell as saying the SSD is faster, but it could be an M2 drive too. By the way, this doesn't even mention M2 drives, but that's somewhere in here as well, because M2 is kind of as fast as a main memory almost. So yeah. So anyways, that's your hierarchy of memories, okay? And so now let's kind of talk again about locality of reference, actually. Although yeah, let's actually, before that, let's just kind of look at this for a second here. So here we go. This is the page where they said it was. I knew I saw it somewhere. Okay, Cmos Technology. That's what registers use. So they're using Cmos. Think of Cmos like your camera sensors. Okay, so they're using Cmos Technology for data storage at register level. Okay, whereas you got your SRAM and your EDRAM, which we already talked about, and DRAM for this stuff for other kinds. Okay. And magnetic disk or magnetic tape for your secondary storage. So, but yeah, CMOS, that's the word that I was looking for earlier with how registers are stored. Now, this is a little bit misleading that they say that it's managed by a compiler, because I disagree with that. It's more of like the compiler is the one that decides which registers store what data, when you compile your program into assembly. So that's probably why they put that in there, so ignore that. But the unit of transfer, it's kind of important too. It's how much data you transfer at a time. With a register, of course, it's just the entire register's contents typically. With cache, it's the same thing again. With main memory, though, you're transferring pieces of it. You're transferring a page of it, as they call it. This is really, you analyze in detail in 370 how this works and different ways of transferring these pages. But as you can see, as you go into bigger sectors, you get a sector. This sector is kind of going to be that partition thing that we were talking about with the allocation. That we mentioned when I was talking about formatting, okay? And who manages it? So the cache is sort of hidden to the OS. The OS doesn't see any of the cache stuff happening. It's sort of happening internally. The OS just needs to pull memory, and it just takes care of it for you. And as a programmer, you don't even see that either. You don't control that. You don't control what goes in the cache and what gets going even to main memory. That is handled again. The only levers that you handle is something at the hard drive level, and then everything else is handled by the computer. Okay, so that's kind of also something that I wanted to point out. Okay, so now we can actually talk about locality of reference here. Okay, so let's see what picture we'll use for this. Yeah, okay, this one's a good picture. So here's the thing. I repeated it earlier today. So we talked about temporal and spatial locality of reference, right? So locality of reference is a very, very powerful thing that we can use so that to sort of, because here's the thing. I guess I'll give you the bigger picture here. So we can't afford to all have amazing hard drives like SSDs or amazing memory like the best possible RAM that we could have, or having tons of cache memory, you know, or having all memory be Cmos memory, which I guess would be the fastest one in theory, I guess, maybe, since I guess that answers your question, since that's what his registers use. I'm going to guess that's faster. So we can't afford that, right? So do we just give up and say, well, we're poor, or technology is not there yet to make it a cheap, you know, accessible to the regular consumer, so let's just give up? No. Locality of reference is going to come to the rescue, okay? And so that effort of locality allows you to take advantage of the memory hierarchy, so you can have a little bit of the entire hierarchy, but still almost have basically the speed of the top one. So when you got your little pyramid, I want to have a little bit of everything, except for the bottom one. Again, that's just useless. But by having a little bit of everything, even though I have just a little bit of memory here and a little bit of memory here, and the majority of my memory is down here, I can still achieve almost the same speed as if I had the best kind of memory. And I would say I can achieve that, I would say 75% of the time. And this has been backed up by papers, right? Research per se, not by papers, research, okay? And so what I want to do is I want to exploit it like this. I want to have some registers. I want to have different layers of cache. I want to have a little bit of main memory, and then the majority of my stuff is going to be down at the bottom with hard drives, okay? So I'm going to exploit this idea of mixing memory together along with locality of reference to almost achieve the speed as if I had all of register or L1 memory, okay? And I will succeed at this. I will succeed at this. So this sounds very snake oil-ish, but it actually works, okay? So let's talk about the design principles for a memory hierarchy, okay? We have locality, which again is how we're going to achieve this. We also have inclusion. Now, what is inclusion? Well, it dictates that all information items are originally stored in levels mn, where n is the level of the most remote from the processor. And then it gets into math. They say that mn is a subset of mi is a subset of mi plus 1 and so on. But what this really means is that we're making a hierarchy and saying that any data that you store at a level up, so if I have some data here, I must have the same data beneath it. So if I'm processing some information here, that some specific spot in memory, that must exist as you go down all the way until you get to the bottom of your hierarchy. Okay? Things get a little bit weird when you go into from the RAM to the hard drive. So like things that you have in RAM may not be in hard drive. However, outside of that, anything from RAM and up, so anything in cache, must exist a copy in every layer. Okay? So that is going to be actually not inclusion, sorry, coherence. That's coherence. So copies of the same data unit in adjacent memory levels must be consistent. If a word is modified in cache, then it must be modified everything beneath that. And that actually causes a lot of issues too. I'll give you a second of that. But then actually, if that's coherence, then what is inclusion? I forgot. Oh, I see. It's the process of copying. So sorry. So inclusion means that as you request information, and by you I mean the CPU, you copy it upwards. Okay, you start copying it closer and closer and closer until I suppose you could say it gets to the CPU itself, which is in the registers. And it's copying, not moving. That's what it means. Okay, so they're kind of confusing between inclusion and coherence, but it means that you copy information down. You don't move it, you copy it. Okay, and kind of the same thing is said with coherence, but the other way around, that it also goes up. So now let's see what we got. What do you mean by grabbing chunks of memory and queuing them next instructions? I think we're talking about locality of reference with that, but I'm not sure. So expand on that. So let's talk about coherence and the problems with that. Okay, we haven't even gotten into actually talking about how we're really going to increase that 75%. But let me give you a situation where trying to do this can become a mess. Okay, so what we're saying is we got RAM, and then we got L3, L2, L1, and then you got, well, actually, I guess a better example of that would be, that's my CPU. Actually, no, that's my processing unit. And here's L3, L2, L1, and registers. And you got main memory. I'll just call it RAM. And sure, why not? We have a hard drive disk, okay, or SSD, whatever. All right. I just don't know how to draw an SSD. It would just be a square or something. So, suppose that I have a piece of information here, okay, and that piece of information needs to be put in the CPU to work with, okay. So I go ahead and I copy it. I copy it down. One way to do this is I could go in here, get the information, and then copy it here. Okay? But then I get other information, and eventually it gets rewritten. But then I need it again. So I got to go all the way back to the RAM to get it. So that's not good, right? So what do? Instead, I take advantage of cache. So if I go ahead and use something here, if I copy it from my memory, when I'm done using it, instead of just deleting it, I end up copying it here. Okay? To the L1 cache. And I'm trying to show you a problem that's going to happen here, okay? But I do this. I copy it to the L1 cache. All right? And so now I'm working, and I do end up needing it again. So perfect. It's closer here. I can more quickly put it back here. And now I'm working with it again. I update it, and so on. Okay? Cool. Now, let's go ahead and upgrade our computer. Let's say that we got multi-core computer. Okay? Multi-core computer means that we're going to have this actually just be one core. So we can have multiple cores. So now I suppose the entire processing unit is going to be, we have a core 2 duo, so 2-core computer. Each of the cores is that. Actually, a better representation of that would be a box right here. Okay? So now, why is this a good representation? Because remember, L3 cache is shared between cores. So I'll put it more like in the middle there. And so this is core 1 and core 2. And each core has its own L1 and L2 cache, right? Right. Okay. So here's the issue. If I just keep copying things back and forth, suppose that this core needs that same piece of information, okay? I updated, I moved things out here. So this information, this address, which let's say this is address 100. And then that address 100 got moved to the register, got processed, it got updated, and we have a copy here. That's the updated copy, Let's say that originally there was a 5 there. And then we took it in here and we plus 1'd it. So now we have a 6. So the L1 cache has a 6, which is still for address 100, okay? And then we do more processing, and then maybe later on we put it back in here from the L1 cache. So it's amazing because L1 cache is faster, so that was better than getting from memory, and now it's a 7. And it also has a 7 here. Suppose that now the second core wants address 100. So it doesn't see it in its L1 cache or L2 cache, doesn't see it in the L3 cache, so it goes into main memory and pulls it. You have a problem. Does anybody see the problem with that? Or having a 5 here from address 100. So questions by grabbing chunks of my rankings, like moving upwards and executing wherever we got there first. So copying into L1 cache is enough. It doesn't have to be copied. Well, that's exactly what I'm saying. That's exactly the last thing you said is exactly the problem that I'm trying to show you here. What is the problem that I've just run into here by copying a 5 into the second core, when the reality is that address 100 should have 7, because that's what I've been working on in core 1. So, do you see the problem that we have here? The problem that we have is that the information in main memory is outdated at this point. And this problem arises when we're dealing with more than one processing unit, or potentially more than one core. And so coherence is required to fix this, which means that if we go ahead and we are updating information, so if we pull in address 5 here, and then we have address 5, and we increase it to 6, you know, we have to propagate that flow, not just, you know, because it might not be enough just to put it here. It has to be propagated to the entire system. So L1, L2, L3, and then RAM, and potentially hard drive. But again, that one is different, because sometimes you don't actually even update that, okay? That's why if you turn off your computer in the middle of nothing, in the middle of like processing, you might lose information, okay? So ignoring the hard drive for that, at least until the RAM level, it has to be updated, okay? And that's because typically, I know that when I drew the pictures of the day, I put the hard drive connected to the processor. That's not really the case usually. The case is that they're only connected to the RAM, and then the RAM is connected to the processor, okay? That's the reality, but you know, I was trying to do an example with the bus being a mess by throwing that in as well. So yeah. If you propagate this, what happens is, suppose it becomes a 7 now. When this becomes a 7, you know, what the L1 cache needs to do, because suppose that this still has a 6 on it, because it just got updated to a 7 like right just now, is it has to communicate between the different L1s and being like, yo, hold on a second, you know, this is not up to date. And it has to propagate, and that's what we'll talk about in the next chapter. It has to make sure it propagates the change all the way, at least. Oh, something happened here. I went into like editing mode. I got like a keyboard appear out of nowhere here. Here we go. All the way at least into the L3 before this guy can read it and update it here as well. Okay, but you still want to update it all the way to RAM, because suppose that this is a quote-unquote supercomputer, just a computer that has more than one chip in it, then these two may share RAM. And so you might have the same problem at the level of RAM. So you have to propagate all the way from the register level all the way up in your hierarchy to make sure that everybody's up to date. And that's where your coherence is. You have vertical and horizontal coherence. And that's what the example they say here, horizontal coherence. There's two L2 caches that share the same L3 cache, have copies of the same block of data. Then if the block 1 of L2 cache is updated, the other L2 cache must be alerted that its copy is obsolete. Okay? The topic of coherence is discussed in future chapters. So because it says to discuss, I guess that's as much as I'll say about that. But at least you already see the problem that can arise with this. And of course, keeping things up to date is going to slow things down, right? Because that's work too. But unfortunately, that's necessary. But again, it's still, the benefits outweigh the costs, okay? So I thought we decided on having 2 or more small caches because it gives better performance. Oh yeah, so yes, so basically what I said, yeah. So yes, this is a performance cost, but again, the benefits outweigh the cost. It's kind of like interrupts, you know, interrupts slow things down, but the benefits still outweigh how much things get slowed down. So it's the same thing with cache. You will see that this is a common pattern in computers. We add things to the computer that slows it down, but we do that because the slowdown that we get is tiny compared to how much we gain from that. Okay, so yes. Okay, each core has a different number. Yes, but that's irrelevant. Okay, so anyways. Okay, so that is going to be what we mean by coherence. So now, let's talk about how to time things, okay? So that's going to be the last thing here that we talk about. And I guess we might actually have to continue next time. And if not, the TA can. So there's an idea of hit or miss. And so looking at our system here, the way that you know whether something is in a certain cache or not is complicated within its own, because you got to search through things and whatnot. So that's not something that I'm going to talk about yet. Okay, we'll talk about when we get to cache, hopefully. But even if we know, if we have some magic ball that tells us whether the data is in a specific cache or up, because it has to be somewhere, right? Otherwise we get an error. But like, let's say that we're looking for some other piece of data here, and this piece of data happens to be at the L3 level but not lower. To get there, technically we have to look through the L1 cache, we have to look through the L2 cache, and then we got to look through the L3 cache and then find it. Okay, so that takes time. Okay, but assuming that we just know that it's an L3 cache, even then we still need to find some time to kind of get there. Okay, and so that's what we mean by hit or miss. We're saying if we get a hit, it means that we look for something in the L1 cache and we found it. If we get a miss, it means we look for something but we didn't find it. So we go up one layer and look again. If we get another miss, we go up one layer, get again. If we get a miss, then we're at the RAM level. So hopefully it's there. Okay? In theory, I guess you could miss that again and look all the way in the hard drive. So that's what we mean by hit or miss. And the idea with hit or miss is to try to compute how long it takes to access data. And why do we want to do that? Because I want to prove to you that by having this layered system of fast memory and slow memory in sort of this hierarchy, I can still achieve the speed of the fast memory by having a bunch of the slow memory too. Okay, and how we're going to do that is with a little formula that's on page 129, and hopefully that one is here, so I don't have to write it. Two layer level memory access, we talked about that, I suppose. We're talking about higher levels because we got multiple caches. Oh, I see. This is the figure one. Let me switch to the PowerPoint one. They don't put the formulas. Oh my gosh, that's so annoying. Hold on. Did I not? Nope, I will have to write the formula. So, right, okay. Let's do that. So we got T of S is equal to H times T of 1 plus 1 minus H times, I don't like using the extra times. Screw that. I like using the dot. Okay, so that's our formula. Now, what do each of these variables mean? T of S is going to be the average access time. T of 1 is going to be the access time of memory 1, which could be a cache. So this example is just for two layers. Okay, so like we have just a level of we have our cache system, and then we have our main memory. Okay, so that's L1 and then main memory. That's all we have. We don't even have registers, I suppose. Okay, so I'll show you how to expand this into multiple levels. So T2 is going to be the access time of the second device, which could be something like main memory. And finally, we have H, which is going to stand for our hit ratio, which means how much time we found what we were looking for in the first one, so in the cache. Okay, so it's important that you guys understand this formula. So we'll spend the last 5 minutes just talking about it, and again, we'll pick this up next time. So basically, the way you want to consider this is, I think it helps if we look at it with numbers. Let's look at it with numbers, okay? So let's go ahead and say, and this is experimental, okay? What you gotta do is you gotta run some data to your computer and figure out how many times we hit and how many times we miss a different level. So let's say that 95% of the time we hit L1 cache, okay? And that's the one where we got the data, okay? If that is the case, then we would say 0.95 times the time it takes to access L1 cache. So for now, we'll just say T1 plus 1 minus 0.95 times T1 plus T2. Okay? What is 1 minus 0.95? That's just going to be 0.05. So I think this is a lot easier to look at and understand what's happening when we put those numbers. Okay? So what we're saying is that 95% of the time, we are able to find the data we're looking for in the cache. That means we hit the data, okay? Because of locality of reference or whatever. We're not getting to us to the Y yet. We succeeded in doing it so far, okay? What this means is that in the case of this, we just have to multiply the amount of time it takes for each of the finds. So let's say that it takes 1 nanosecond to find, or here, no, let's 1 second, just to make life easy. Let's say it takes 1 second to find something in the M1, so that's the L1 cache or whatever. And then in main memory, let's say that it takes, so T1 is equal to 1 second, and let's say T2, it takes 10 seconds, okay? Because it's slower, so main memory is slower, okay? So if we go ahead and do that, let's plug it in like that. So 0.95 times, and I guess I'll put it here, H is equal to 0.095, so you know. You can say 0.95 times 1 second plus 5% of the time, we don't find what we're looking for in the L1 cache. We find it in main memory. So that means we have to add in the 10 seconds, but we also have to add in the time it took us to search in the L1. Or not just to search, but to access it, because that's the access time. Again, we're not talking about how long it takes to actually search through it, just to access it. You know, say that we can find it instantly. If you can find it instantly, if it's there, that means that we have no search time. But we still need to have to access it, okay? And that takes time. Access and search, different things. If we go back to the beginning of today's lecture when we're talking about those three things, you know, the cycle and then the access, latency and all that, that's what we're talking about here. So that means we have to do 10 plus 1. So this basically becomes 0.95 plus 0.05 times 11. Okay? What's this multiplication, guys? Somebody do the multiplication for me while I answer the question here. Oh no, that was the question we already had. So what's this equal to? Otherwise, you guys gonna make me do this? So let's see, that's 5, 0, 0, and then we get 5, 0, 0, and so that becomes 5, 5, 5. So it's 0.55, I think, right? Is that right? You guys, that what you guys got? Okay, cool. You guys got the same. Nice. So then we get 0.95 plus 0.55. Okay? Now add those two together. You're going to get 1.5, I think. Yeah, 1.5, okay? So that means that our average access time is 1.5. Now let's look back. The L1 cache access time, T1, that was 1 second. The main memory access time, that was 10 seconds. We got 1.5 seconds on average. Yes, it's not 1 second, our ideal time, but it is definitely closer to our ideal time than it is to our main memory time, right? So if we have that hit ratio of 0.95, we don't really lose much efficiency from this two-layer system, even though we get the extra capacity that this can give us. That's, of course, with 0.95, but that's really ambitious, right? Well, I'm here to tell you that 0.75 can easily be achieved, but even 0.90 is achievable. We'll talk about that next time. I'll leave it for now here, and we shall continue tomorrow. By the way, disclaimer, tomorrow I'm taking my dad to the airport at 10 a.m., I think. So I should be back by 10, and I'm going to stop by UNLV to pick up some papers probably. So I should be back at 10:30, but in the rare case that something happens, I'll send you guys a message on Discord in the case that I have to delay class or cancel class and then just record it and post it or something. But I should be back by 11:20, okay? But I'm just saying that because I have not I haven't left my house in a long time, and I don't know what kind of situation I'll run out there. But I should be back by 11:20. Okay, so I'll keep you. I actually have to drop my dad off at 10 at the airport, so it gives me an hour to come back essentially. So just giving a disclaimer in case that something happens. Okay, so just keep track on Discord. But cool. All right then. Lecture will happen. Worst case scenario, I'll get like Sam to cover me or something. So I should be back though. But you never know, flat tire or something. So cool. All right then. I'll see you guys tomorrow then. Hopefully, you know, unless bad things happen, we shall continue talking about this. I'll post the readings on Canvas if I to start reading. I will make you guys start reading chapter 5. I don't know yet how much of it I'll make you read. I have to see. But if you can read the entire chapter, that'd be great. But if not, then I think probably 5.2, 5.1 and 5.2 you want to read, I would say. So, but I'll post it on Canvas later once I kind of look at it myself. I want to see it first. So, cool. See you guys. Thanks.